Hello there, and welcome to the SleepFast Science channel. Tonight, we'll take a quiet journey into the farthest reaches of space, exploring some of the most distant galaxies ever discovered. These enormous gatherings of stars were shaped by gravity and powerful cosmic forces long ago, stretching back to the earliest chapters of the universe. When we look toward these galaxies, we are not only looking across vast distances, we are also looking into the deep past, to a time when the universe was still young and slowly becoming what it is today. Distant galaxies hold gentle stories of creation and transformation. They show us how matter slowly gathered across space, how the first stars began to shine, and how the earliest cosmic structures formed out of swirling clouds of gas and dust. Some galaxies glow with the bright energy of youth, filled with newly forming stars. Others appear calmer and quieter, having passed through their most active years long ago. Each one offers a small clue about how the universe evolved and how our own cosmic home eventually came to exist within this vast and ancient story. If you enjoy these peaceful explorations, you're welcome to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy explorer at a time. But for now, there is nothing you need to do. Allow your shoulders to relax. Let your breathing slow and deepen. Allow the day's thoughts to drift away like distant clouds. As your eyes grow heavier and your mind becomes quieter, join me as we gently wander through the cosmos together. Let's begin. The farthest galaxies we can observe are also the earliest chapters of the universe's history. When a telescope captures their faint light, it is receiving a message that began its journey billions of years ago. That means distance and time are woven together. Nearby galaxies show the universe during its later, calmer years, but the most distant ones reveal it during its restless childhood, when everything was smaller, hotter, and still taking shape. Astronomers build a kind of cosmic timeline by comparing galaxies at many different distances. Each one represents a different moment in the long story of the universe. Through these observations, we can watch stars being born, see galaxies slowly change shape, and observe the first heavy elements spreading through space from ancient stellar explosions. It is history written in light. And the remarkable thing is that this history has never disappeared. The pages of the universe's past are still arriving here, night after night, carried by ancient photons that have traveled across unimaginable distances. Some of the galaxies we observe today are so far away that their light began its journey before our sun even existed. Our sun is about 4.5 billion years old, yet many galaxies shine from a time long before that. Back then, the Milky Way itself was still forming. The universe was simpler. Many of the elements we rely on today did not yet exist. Early generations of stars had to create them first. Inside the hearts of those ancient stars, lighter elements fused together to form heavier ones. When those stars reached the ends of their lives, they exploded and scattered those new elements into space. Over immense stretches of time, those enriched atoms became the building blocks of planets, oceans, and eventually living beings. When we observe a galaxy from that early era, we are seeing a universe that had not yet learned how to create worlds like our own. That is part of what makes distant galaxies so fascinating. They show us the long chain of events that had to unfold before we could ever exist. A single deep image of the sky can contain thousands of galaxies. A patch of sky that looks empty to our eyes can be crowded with distant galaxies when a telescope studies it patiently. Deep space images are created by collecting faint light for many hours. Telescopes gather tiny particles of light, one by one, stacking them together until faint galaxies slowly appear. In some famous deep-field images, the portion of sky being studied is smaller than the width of your little finger held at arm's length. Yet within that tiny window of space, astronomers can see countless galaxies, spirals, ellipticals, and irregular shapes, each at different distances and stages of life. Some are close enough to show beautiful structure and detail. Others are little more than soft smudges of light. Together, they reveal something extraordinary. The universe is not sparsely dotted with galaxies. It is filled with them. Once you understand this, the night sky never quite feels empty again. Many distant galaxies appear stretched or distorted because gravity bends their light. On the largest cosmic scales, gravity can behave like a natural lens. When a massive galaxy or cluster lies between us and a more distant galaxy, its gravity curves space itself. The light from the background galaxy must travel along these curved paths. To us, the distant galaxy may appear stretched into glowing arcs, duplicated into multiple images, or even wrapped into delicate rings of light. These shapes are not illusions. They are the visible signatures of gravity shaping the path of light across the universe. By carefully measuring these distortions, astronomers can map the invisible mass within galaxies and clusters, even the mysterious matter that produces no light of its own. This phenomenon, known as gravitational lensing, can also magnify distant galaxies, allowing us to study objects that would otherwise remain far too faint to detect. In this way, gravity becomes both a sculptor and a guide, helping us see deeper into the cosmos than our instruments alone could manage. The most ancient galaxies often appear reddish in color because space itself stretches their light. As the universe expands, the waves of traveling light become stretched into longer wavelengths. Light that once shone in bright blue or ultraviolet can arrive at Earth shifted toward the red. Because of this, astronomers often rely on infrared telescopes to observe the earliest galaxies. These instruments are designed to detect light that has been stretched far beyond the visible range. Red colors can also tell us something about the stars within a galaxy. Older stars tend to be cooler and redder than young, hot stars. By observing galaxies through different filters and comparing the colors they produce, astronomers can estimate their ages and determine when their stars first began to shine. Sometimes, a faint reddish glow marks the presence of galaxies that formed incredibly early in cosmic history. In the young universe, galaxies frequently collided and merged with one another. Back then, galaxies were closer together, and their paths crossed more often. When two galaxies drifted near each other, gravity slowly pulled them into long, graceful encounters that could last millions of years. Tidal forces stretched out long streams of stars and gas. Clouds of gas collided and compressed, often triggering bursts of star formation. These events rarely destroyed galaxies completely. Instead, they reshaped them. Two smaller galaxies might merge into one larger system. A thin disk of stars might become thicker and more chaotic. Gas could be drawn toward the center, igniting brilliant waves of new star formation. When astronomers observe very distant galaxies, they often see unusual and distorted shapes that reflect this energetic period of cosmic growth. Even today, many galaxies carry subtle traces of these ancient meetings. A galaxy's color can also reveal whether it is actively forming stars or resting quietly. Galaxies filled with newborn stars tend to glow with a soft bluish light because young stars burn very hot and bright. When star formation slows, those bright blue stars fade quickly, leaving longer-lived red stars to dominate the galaxy's light. By measuring these color patterns carefully, astronomers can estimate how actively a galaxy is creating new stars. Some galaxies appear lively and energetic, still building new generations of stars. Others appear calm and settled, like quiet towns long after a festival has ended. Even cosmic dust leaves its own signature, gently reddening light as it passes through clouds of gas and particles. With only a few bands of color, astronomers can learn whether a galaxy is actively forming stars, resting peacefully, or hiding its activity behind veils of dust. In the early universe, galaxies grew quickly through repeated mergers and steady supplies of fresh gas. Small galaxies were common, and gravity constantly pulled them together. When galaxies met, their stars rarely collided because the space between them is enormous. But their clouds of gas interacted strongly, compressing and heating as they passed through one another. At the same time, fresh gas flowed inward from the surrounding cosmic web, feeding new waves of star formation. This steady supply of material allowed young galaxies to grow rapidly. Over time, many small clumps of stars and gas merged into larger, more organized galaxies, like the ones we see around us today. By studying the shapes, motions, and chemical signatures of distant galaxies, astronomers can still read the story of this early cosmic growth, written across the quiet light of the universe. The story of distant galaxies is a story of construction under pressure. A slow cosmic building project where new materials kept arriving, and the blueprint kept changing. Galaxies did not appear fully formed. Instead, they grew gradually, gathering gas, dust, and stars across vast stretches of time. Gravity pulled matter together, while powerful cosmic events reshaped the structures again and again. Even today, astronomers are still learning how these enormous systems came to be, and sometimes the most active galaxies are hidden in plain sight. Many distant galaxies are wrapped in thick clouds of cosmic dust. This dust is made of incredibly tiny particles, closer in size to smoke than grains of sand. Yet despite its delicate appearance, dust is remarkably effective at blocking visible light. In distant galaxies, these dusty clouds can surround regions where new stars are forming. Entire stellar nurseries, blazing with activity, can be hidden almost completely. To a telescope that observes only visible light, such a galaxy may appear faint, quiet, even unimpressive. But when astronomers observe those same galaxies using longer wavelengths of light, the story changes. Dust absorbs energetic light from young stars. It warms slightly, and then releases that energy again in the form of infrared and millimeter radiation. Telescopes designed to detect those wavelengths can suddenly reveal galaxies bursting with star formation. Galaxies that once seemed dim and quiet can turn out to be extraordinarily active, building new stars at astonishing rates. This is one of the reasons our understanding of the universe has continued to evolve. As new kinds of telescopes were developed, astronomers began seeing the universe in entirely new ways. Dust, it turns out, was not simply decorating galaxies. It was hiding some of the most energetic places in the cosmos. And by learning to see through that dusty veil, astronomers began to uncover a far more complete picture of how galaxies grow. For a long time in cosmic history, star formation was far more intense than it is today. There was a period when the universe seemed to be bursting with stellar activity. Astronomers sometimes refer to this era as cosmic noon, a time when galaxies across the universe were producing stars at extraordinary rates. During this period, galaxies were rich in cold gas, the raw material needed to form new stars. That gas could collapse easily under gravity, creating dense regions where new stars ignited. Many galaxies were also interacting and merging with one another. These encounters compressed clouds of gas, triggering brilliant waves of starbirth. Across the universe, countless galaxies were lighting up with new stars. It was something like a cosmic fireworks season. But over time, that energetic era began to quiet down. The supplies of cold gas slowly diminished. Some gas was consumed in the process of star formation. Some was heated by energetic events inside galaxies, and some was pushed away by powerful outflows. Gradually, the average rate of star formation began to decline. The universe did not stop making stars. It simply became calmer, slower, more measured. Understanding when this peak occurred helps astronomers explain why galaxies appear the way they do today. Many large galaxies are now filled mostly with older stars. Their brightest years of star formation lie far in the past. And when we look into the night sky, we are still receiving faint light from that more active era of the universe. Modern telescopes allow astronomers to see many stages of this story at once. A single telescope image can contain galaxies from very different moments in cosmic history. In one region of the sky, a nearby galaxy might reveal crisp spiral arms, well-organized structures where stars form in calm neighborhoods. In the very same image, a much more distant galaxy may appear smaller, rougher, and less organized. But that difference is not caused by the telescope. It is caused by time. The nearby galaxy shows us the universe in a more mature stage. The distant galaxy shows us the universe when it was younger. Different distances mean we are seeing different ages of the cosmos. The telescope simply records whatever light arrives. This ability allows astronomers to compare galaxies across billions of years using the same instruments, the same techniques, and the same observations. It is a little like holding a family portrait that includes infants, adults, and elders, all in one frame. Seeing those different stages together helps reveal patterns and sometimes surprising connections. In this way, a single observation can become a cross-section of cosmic evolution. Many distant galaxies appear only as faint smudges in deep images of the sky. Some barely stand out from the darkness behind them. They may look like soft fingerprints against black velvet. But that faint appearance does not mean those galaxies are small. It simply means they are incredibly far away. As light travels across immense distances, it spreads out in every direction. By the time it reaches our telescopes, the glow of a galaxy has been diluted across an enormous sphere of space. Add to that the effects of dust, aging stars, and the limits of our detectors. And even a massive galaxy can appear very subtle. Astronomers study these faint traces of light carefully. By measuring a galaxy's shape, its color, and how its brightness changes across an image, they can estimate how many stars must be present to produce that glow. And sometimes the result is astonishing. A tiny blur of light, barely visible in a telescope image, may represent a galaxy containing billions of stars. The universe often hides its grandest gatherings inside its quietest specks of light. Some galaxies shine with extraordinary brightness because something powerful is happening at their centers. At the heart of many galaxies lies a supermassive black hole. When gas begins falling toward one of these black holes, it does not disappear quietly. Instead, the gas spirals inward, forming a rapidly spinning disk. Friction and pressure heat this disk to incredible temperatures. The result is a region that can shine with staggering power. In some cases, the light from this central engine can outshine all the stars in the surrounding galaxy combined. When that happens, the galaxy's core becomes visible across billions of light years. These brilliant objects are known as quasars. Unlike stars, which shine through nuclear fusion, Quasars are powered by gravity itself. As matter falls toward the black hole, enormous amounts of energy are released. Sometimes the brightness of a quasar changes over weeks or months. That gentle flickering provides astronomers with clues about the size of the region producing the light. When we observe one of these brilliant cores, we are witnessing a galaxy with an active and powerful heart. Not all galaxies remain active forever. Some eventually become what astronomers call quenched galaxies. A quenched galaxy is not truly dead. Its stars continue shining for billions of years. But something has changed. The birth of new stars has slowed, or even stopped. The galaxy may have used up much of its cold gas, or the remaining gas may have been heated so strongly that it can no longer collapse into new stellar nurseries. Sometimes powerful events near the galaxy's center push gas outward, preventing fresh material from settling back in. Without that fuel, star formation gradually fades. The galaxy becomes dominated by older stars. Astronomers recognize these systems by studying their colors, their spectra, and the absence of bright young stars. Quenching represents a turning point in a galaxy's life. It is the moment when a galaxy stops adding new voices to its stellar chorus and begins to age with the stars it already has. Despite the chaos of the early universe, some distant galaxies already show beautiful spiral shapes. Spiral galaxies often feel like the polished result of long cosmic evolution. Their graceful arms seem as though they should require stability and time to develop. That is why it can be surprising to discover spiral galaxies very far away, at a time when the universe was younger and more crowded. Spiral arms are not solid structures. They are patterns created by motion, formed as stars and gas orbit within a rotating disk. For a spiral galaxy to exist, its gas must settle into a relatively flat, rotating structure. Seeing these spirals early in cosmic history suggests that some galaxies found their balance sooner than astronomers once expected. It also raises intriguing questions about how those galaxies managed to remain stable in a universe filled with interactions and mergers. By studying these early spirals, astronomers learn how galactic disks survive, how order can emerge from turbulence, and how galaxies like our own Milky Way may have begun taking shape long before our solar system existed. Many early galaxies, however, look very different. Instead of smooth structures, they appear clumpy and irregular. This is because their gas collapses into enormous knots, creating giant regions where stars form in massive clusters. These clumps can contain vast numbers of young stars, blazing brightly in the early universe. Over time, those clumps may merge, settle, and gradually form the more familiar shapes we see in galaxies today. And as we continue to observe deeper into space and farther back in time, the quiet light of distant galaxies continues to reveal new pieces of this remarkable story. A story written across billions of years, carried by ancient light, and slowly arriving here, night after night, from the farthest reaches of the cosmos. Let's begin by imagining a distant galaxy, not the kind we often see in photographs of nearby space, with smooth spiral arms turning gently around a bright center. Instead, imagine something more chaotic. Many distant galaxies do not look like neat spirals at all. When astronomers observe them through powerful telescopes, they often appear as scattered islands of light, bright patches spread across a darker background. At first glance, these shapes can seem messy, unfinished, almost irregular. But those glowing islands are not random. Each one is usually an enormous region where stars are being born. These star-forming regions can be far larger than the ones we see in nearby galaxies today. Early galaxies carried immense reservoirs of gas, the raw material from which stars are made. In those young galaxies, that gas did not always settle into tidy structures. Instead, gravity could cause the gas to become unstable. Large clouds would collapse under their own weight, breaking into massive clumps. Inside each clump, stars could form in powerful bursts. Thousands, sometimes millions, of young stars igniting within a relatively small region. When that happens, the clump shines brightly, like a beacon across space. These glowing patches are the stellar nurseries of the early universe. They are signs that galaxies were still in the middle of building themselves, and over time, those clumps do not remain in one place. Slowly, almost imperceptibly, they move. Some drift through the galaxy. Some merge with neighboring clumps. Others gradually migrate toward the galaxy's center. As they move and combine, they help reshape the structure of the entire galaxy. Astronomers study this clumpy appearance very carefully. Those bright knots of light hold clues about how galaxies formed their central regions, and how chaotic clouds of gas eventually settled into the more organized systems we see today. So when we look at a clumpy galaxy, we are not seeing something incomplete. We are seeing growth in action, a galaxy still hard at work, transforming raw cosmic material into starlight. In a way, these clumps are enormous stellar workshops, places where gravity gathers gas, compresses it, and turns it into stars. They are visible signs of a young galaxy doing the heavy lifting of construction, not a finished design, but a process still unfolding. And while some distant galaxies appear clumpy and spread out, others present a different kind of mystery. Some galaxies appear surprisingly compact. Through a telescope, they may look small, almost modest. But when astronomers measure their gravity, they discover something remarkable. These galaxies contain enormous amounts of mass packed into a tiny region of space. Imagine squeezing the mass of a large galaxy into a volume only a fraction of its expected size. In such galaxies, stars are crowded close together. Their orbits move rapidly, and the internal motions within the galaxy can be intense. Astronomers detect this compactness by studying how the galaxy's light is distributed. If the light is tightly concentrated, it suggests that many stars are gathered within a small area. They also examine spectral lines, subtle fingerprints within the light, which reveal how quickly stars and gas are moving. Fast motions often mean strong gravitational forces, and therefore large amounts of mass. These compact galaxies are fascinating because they may represent an early stage in the lives of today's giant galaxies. They could be young galaxies caught during a brief, intense phase before they expanded through later growth. Over billions of years, mergers and the addition of new material may cause them to grow larger and more spread out. But at this early stage, they are dense, energetic, and tightly packed. Astronomers sometimes wonder how such systems formed. Did enormous clouds of gas collapse quickly under gravity? Or did early galaxy mergers funnel huge amounts of material inward toward the center? However they formed, these compact galaxies reveal something important. The universe can build enormous structures surprisingly quickly, and size alone does not always reveal a galaxy's true significance. Some of the most powerful systems in the early universe may have been hidden within surprisingly small shapes. Over time, many galaxies change dramatically. Some of the largest galaxies we observe today are known as elliptical galaxies. These galaxies often appear smooth, round, and calm. At first glance, they look quiet, almost serene, but their histories are often anything but peaceful. Astronomers believe many giant elliptical galaxies formed through repeated collisions between smaller galaxies. When galaxies merge, the orderly rotation of stars within their disks can be disrupted. Instead of moving along neat circular paths, stars begin traveling in many different directions. Over long periods of time, this mixing of stellar orbits creates the smooth, rounded appearance typical of elliptical galaxies. Yet even within these calm shapes, traces of the past can remain. Astronomers sometimes find faint shells, ripples, or subtle distortions in the light of elliptical galaxies. These delicate patterns are leftovers from ancient encounters, like wrinkles that never quite disappear. Elliptical galaxies also tend to contain older stars. This suggests that most of their star formation happened long ago, before the galaxy settled into a quieter phase. Today, they glow softly with ancient starlight, slowly aging over billions of years. Astronomers often study elliptical galaxies as the endpoints of long cosmic journeys. They are the products of many earlier chapters, mergers, interactions, bursts of star formation. They remind us that a calm appearance does not always mean a calm past. Sometimes the smoothest galaxies are the ones that survived the most upheaval. But not all galaxies are giants. Some of the most important galaxies in the universe are actually quite small. These are known as dwarf galaxies. Compared with massive galaxies like the Milky Way, dwarf galaxies contain far fewer stars. Their gravitational pull is weaker. And because of that, they respond more dramatically to events around them. Gas can be pushed out of dwarf galaxies more easily. Star formation may begin and stop in bursts, and their chemical composition often remains simpler for longer periods of time. In many ways, dwarf galaxies act like cosmic time capsules. Some preserve evidence of early star formation that may have been erased in larger galaxies that experienced many mergers. Astronomers believe dwarf galaxies may also serve as building blocks for larger galaxies. Over time, small systems can be pulled in and absorbed. Their stars become part of a growing galaxy. Their gas fuels new generations of stars. By studying dwarf galaxies, counting them, measuring their motions, and examining their stars, astronomers test ideas about how galaxies assemble, and about how invisible matter shapes the universe's structure. If we want to understand how the universe builds galaxies, we cannot ignore the small ones. Sometimes the smallest galaxies preserve the clearest records of the past, and sometimes these small galaxies are slowly torn apart. Gravity is not always gentle. When a dwarf galaxy orbits a larger one, the gravitational pull can stretch it. Repeated close passes may gradually peel stars away. Those stars do not vanish. Instead, they form long, delicate streams that wrap around the larger galaxy. These stellar streams can stretch across enormous distances. Thin rivers of light, tracing graceful arcs through space. They are beautiful, but they also tell an important story. They reveal that galaxies are still growing, still capturing smaller companions, still assembling themselves piece by piece. These streams also help astronomers map invisible matter. The shapes and paths of the streams respond to the gravitational field surrounding the larger galaxy. By tracing those paths carefully, astronomers can learn about the hidden mass shaping the system. Even long after the dwarf galaxy itself has dispersed, its stars continue tracing its former orbit, writing the memory of that encounter across the sky. Our own galaxy, the Milky Way, is just one island within a vast cosmic ocean. Because we live inside it, it can feel like the center of everything. But modern observations have revealed a different truth. Galaxies fill space in every direction. Even a region of sky that appears empty may contain countless distant galaxies. Each one is its own complex ecosystem. Each one has its own story of starbirth, chemical change, and gravitational drama. Some galaxies are small and faint. Others are enormous and ancient. When we call the Milky Way an island, we also acknowledge something humbling. Islands can have neighbors, and the cosmic sea surrounding them can stretch endlessly outward. When we look into the night sky, we are not just seeing distant lights. We are seeing distant places. And much of that light began its journey billions of years ago. Looking outward is also a way of looking backward in time, a way of meeting the larger universe. Many galaxies do not live alone. They gather in groups, held together by gravity. Within these groups, galaxies influence one another over immense spans of time. They pass close enough to tug on each other's stars. They stir up clouds of gas. Sometimes they merge. Sometimes they reshape one another without ever fully colliding. Within a galaxy group, some galaxies grow dominant, while others become satellites orbiting their larger neighbors. Repeated encounters may gradually strip material away from the smaller members, changing them slowly over time. Our own Milky Way belongs to such a group, and by studying distant galaxy groups, astronomers learn how different cosmic neighborhoods evolve. On an even larger scale, galaxies gather into clusters. A galaxy cluster is like a city on a cosmic scale. It may contain hundreds, or even thousands, of galaxies, along with vast clouds of hot gas and enormous amounts of invisible mass. Inside a cluster, galaxies move at tremendous speeds. Close passes are common. These interactions can distort galaxies, strip away their gas, and leave some with little fuel for forming new stars. Clusters also serve as powerful tools for astronomers. Their immense gravity can bend light from galaxies far behind them, magnifying distant objects that would otherwise remain too faint to see. By mapping galaxy clusters, astronomers learn how matter gathers across the universe and how the largest structures in existence slowly take shape. Between these crowded cosmic cities lie enormous regions where galaxies are rare. These are called cosmic voids. If clusters resemble bustling cities, voids are more like quiet countryside. They can stretch across tens of millions of light years with very few galaxies. Voids are not completely empty, but the matter within them is spread thinly across vast distances. Their existence tells us something profound about the universe's history. Long ago, tiny differences in density appeared after the Big Bang. Over time, gravity amplified those differences. Dense regions pulled matter inward, eventually forming galaxies and clusters. Meanwhile, emptier regions became even emptier, expanding into the vast cosmic voids we observe today. And across this immense landscape, clusters, groups, galaxies, streams, and voids, the universe continues its quiet evolution. Stars ignite, galaxies merge, structures slowly grow, all unfolding across billions of years. In a cosmos far larger and older than we can easily imagine. And as you rest here, listening quietly, the light from those distant galaxies is still traveling, still crossing the depths of space, still carrying the story of the universe toward us, one photon at a time. Dense regions of the early universe slowly gathered more matter. Little by little, gravity pulled material inward, and those denser regions grew heavier, richer, and more crowded. Over immense stretches of time, They became clusters. Meanwhile, the less dense regions slowly lost that quiet tug-of-war. Matter drifted away from them, and those regions gradually emptied out, becoming the vast cosmic voids we see today. When astronomers map these voids, they are not simply measuring absence. They are studying shape, history, and growth. They are tracing how gravity pulled matter together and how cosmic expansion stretched the universe outward. The size and shape of voids can even help test our biggest ideas about cosmology, because voids depend on how the universe expands and on how matter gathers into structure. And that is one of the most beautiful surprises in astronomy. Even emptiness has a pattern. Even the quietest places in the cosmos still carry information. When we step back and look at the largest scales of all, we find that galaxies are not scattered randomly through space. Instead, they trace a vast cosmic web. Across unimaginable distances, galaxies gather along filaments and broad sheets, connecting clusters to one another. Together, those connections form a great network stretching across the observable universe. You might picture it like bright beads resting on invisible threads. Those threads exist because matter flowed along certain pathways under gravity, guided by tiny ripples that were present in the early universe. Gas followed those same pathways, and gas is the ingredient that makes stars. So the cosmic web is not only a map of where galaxies are, it is also a map of where galaxies can be fed, where fresh material can flow, where future stars can be born. Astronomers reveal this web by surveying enormous volumes of space. They measure the positions of millions of galaxies and slowly turn those points of light into a three-dimensional map. The result is both beautiful and deeply useful. It helps explain why clusters tend to sit where filaments meet, why voids open between them, and why the universe looks less like a fog and more like a network. Our own galaxy belongs to this web, too. The Milky Way is not floating alone. It rests along one strand of this larger structure, carried within the same vast design. And beneath this visible pattern lies something even stranger. A galaxy's stars, glowing softly in the dark, are only part of the story. Most galaxies seem to sit inside much larger halos of unseen mass. This invisible material is called dark matter. It does not shine. It does not absorb light. And yet, it exerts gravity. That gravity helps pull ordinary gas inward. It helps gather matter into growing clumps, and it helps hold that gas in place long enough for stars to form. Without this hidden framework, many galaxies would have struggled to assemble as efficiently as they did. Dark matter halos also influence the shapes of galaxies and the motions of their stars. In computer simulations, structure often begins when dark matter gathers first. Then, the visible material follows that hidden gravitational blueprint. Astronomers cannot photograph a dark matter halo directly, but they can detect its effects. They see it in the motions of stars. They see it in the bending of light. The idea is simple, and the implications are enormous. Much of the universe's architecture appears to be built from something we cannot see. We learn that it is there because of how everything else behaves. One of the clearest clues came from galaxy rotation. If astronomers measure only the stars and gas they can see, many galaxies should not hold together as well as they do. The outer stars move too quickly. There does not seem to be enough visible gravity to keep them bound, and yet they remain in orbit. When scientists carefully measured how orbital speed changed with distance from a galaxy's center, they expected the speed to decline. But that is not what they found. Instead, the outer parts kept moving fast, again and again, across many galaxies. The same pattern appeared. That stubborn speed suggests that a much larger reservoir of mass surrounds the visible galaxy, a broad, extended halo, a hidden structure reaching far beyond the stars we can easily see. And this conclusion does not depend on one galaxy or one method. It appears across many systems and through many observations. Dark matter became the simplest explanation that fits the pattern. The result is wonderfully strange. The visible part of a galaxy is almost like the lit windows of a city at night. Beautiful, bright, easy to notice. But most of the mass that shapes the city's gravity lies in the darkness around it. Another way astronomers detect dark matter is through gravitational lensing. When a massive object lies between us and a more distant galaxy, its gravity can bend the light coming from behind it. That bent light can appear as long arcs around galaxy clusters. Sometimes, when the alignment is especially precise, it can form a nearly perfect ring. These shapes are not random. Their curves depend on how mass is distributed in the foreground object. That includes the ordinary matter we can see, and the much larger contribution from dark matter. By modeling these arcs and rings, astronomers can reconstruct maps of mass, and often they find that the visible galaxies account for only a small fraction of what is required. This is part of what makes lensing so powerful. Gravity bends light whether the mass is glowing or not. So lensing allows distant galaxies to act like backlights. They illuminate the invisible structure in front of them. In that sense, geometry becomes a weighing scale. Each arc is a signature of hidden mass, written in starlight. Lensing can do something else as well. It can magnify very distant galaxies. Sometimes a faraway galaxy is simply too faint to study clearly. Its light is real, but it arrives in too small a trickle. Gravitational lensing can change that. When a massive foreground object focuses the light, the background galaxy can appear brighter and stretched across the detector. That stretching can reveal details that would otherwise blur into a tiny dot. It can even make spectroscopy possible, allowing astronomers to study chemical fingerprints and the motions of gas in galaxies that would otherwise remain beyond reach. This is not a trick of editing. It is nature itself providing a larger lens. Through curved space, the image becomes more complex, yes. It must be modeled carefully, but the reward is extraordinary. Lensing opens windows onto the early universe. It lets us study galaxies that are intrinsically small, very young, or hidden behind dust. It is one of the rare moments in science when the universe seems to lend us an instrument, and we slowly learn how to use it. Sometimes lensing produces more than one image of the same distant galaxy. A strong gravitational lens can split one background source into 2, or 4, or even more images. Each image follows a different path through curved space, and those paths are not always the same length, so the light can arrive at different times. If the distant object changes brightness, astronomers might see the change appear in one image first, and later in another. The sky becomes a natural timing experiment. By measuring those delays, astronomers test their lens models and learn about the expansion of the universe itself. In rare and wonderful cases, an event can be seen more than once, with later appearances predicted in advance. That is one of the most mind-bending gifts of lensing. You are not only seeing the same object multiple times, you're seeing it at different arrival times, as though the universe has sent one message along several different roads. Some of the brightest distant objects used in these studies are quasars. A quasar can outshine its entire host galaxy for a time. That seems almost impossible until we remember what is producing the light. It is not a swarm of stars. It is matter falling inward toward a supermassive black hole. As gas spirals inward, gravity squeezes it tighter and tighter. The gas heats up. It crowds into a brilliant, energetic region, and there it can radiate fiercely across the spectrum. The glow can become so intense that the surrounding galaxy is hard to see, like a city skyline fading behind the glare of a stadium floodlight. Quasars were once deeply mysterious. They looked like stars, but they did not behave like stars at all. Their great distances revealed them to be cosmic lighthouses, visible from across immense reaches of space. And they teach us something humbling about scale. A region no larger than our solar system can dominate the light of a galaxy stretching across hundreds of thousands of light years. Because quasars are so bright, they help astronomers study the early universe. When quasar light travels toward us, it does not pass through complete emptiness. It crosses thin gas between galaxies, and that gas leaves tiny marks in the quasar's spectrum. Little absorptions. Tiny bites of missing light. Those marks become a record of what the universe was like along that line of sight. They can reveal how much neutral hydrogen remained. They can show how the gas was enriched by earlier generations of stars. They can help us understand how cosmic structure grew. In this way, a quasar becomes more than an object. It becomes a backlight for a long invisible landscape. By studying many quasars across the sky, astronomers build a patchwork view of intergalactic matter at different distances, and therefore at different times. This helps reveal when the universe became transparent to ultraviolet light. It helps reveal how early structures formed. It is a clever and elegant method. Instead of trying to see faint gas directly, we let a distant beacon carry the evidence to us. And in some galaxies, the bright central regions are still active today. These active galactic nuclei can flicker as their black holes feed. That flickering is a gift, because rapid changes in brightness suggest that the glowing region must be compact. A very large region could not brighten or dim all at once. So astronomers watch these variations carefully. They compare changes across different wavelengths. They measure how long one band of light takes to echo another. And from those echoes, they begin to reconstruct the hidden structure near the black hole. So even a flicker, even a small change in light, can become a clue, a quiet signal, from one of the most powerful engines in the universe. And as all of this unfolds, clusters and voids, webs and halos, arcs of light and distant quasars, the universe continues to reveal itself slowly. Not all at once, but gently, through patterns, through gravity, through light arriving from far away. And perhaps that is part of what makes it feel so peaceful. Even the largest structures in existence were shaped gradually. Matter gathering, light bending, galaxies forming, voids opening, everything unfolding across timescales so vast that even the most dramatic events become quiet in the telling. So as you picture this great cosmic web, with its glowing clusters, its long filaments, its deep, silent voids, you might let your thoughts slow as well. You might imagine yourself drifting above it all, watching the structure of the universe appear like a delicate pattern in the dark, bright in some places, quiet in others, but meaningful everywhere. That delay is more than a curiosity. It becomes a kind of ruler, a quiet measuring tool, made of light and time. By studying that delay, Astronomers can estimate the spacing between the glowing regions near a black hole. They can trace the distance between the hot inner disk and the surrounding clouds of gas, which brighten in response when the central region changes. This technique is called reverberation mapping, and it allows astronomers to estimate the mass of a black hole, even when the region itself is far too small and distant to appear as a clear image. So the story is not still. It is not static. A black hole does not feed with a perfectly steady rhythm. It feeds unevenly, in clumps, in pulses, sometimes gently, and sometimes dramatically. When the core flickers, it is as if the universe is showing us that the engine is alive, active, adjusting in real time. And in some galaxies, that activity does not stay near the center. It reaches outward, far outward. Some active black holes launch narrow jets of particles that race away at nearly the speed of light. These jets can punch through the galaxy that hosts them, then keep going, stretching far into intergalactic space. Sometimes they extend so far that they dwarf the diameter of the galaxy itself. As they travel, they glow through a process called synchrotron radiation. This happens when fast-moving charged particles spiral around magnetic fields, tracing invisible lines with visible energy. At the far ends of these jets, enormous radio lobes can inflate like cosmic balloons. And where the jet slams into surrounding gas, bright hotspots can appear, marking the impact. So even when a galaxy's stars appear calm and quiet, the jets reveal something intense and focused happening at its center. They make the black hole visible in a different way, because the black hole itself is dark. It does not shine, but the jet is like a signature written across space, showing where energy is being carried, far beyond the place where it was first released. In the clearest cases, astronomers can trace the full path of a jet, from the bright core all the way out to the distant lobes, like following a glowing map through the dark. And these jets do more than shine. They can shape the future of a galaxy. A galaxy may contain plenty of gas and still form very few new stars, not because the fuel is missing, but because the gas is too warm, too stirred up, too turbulent to collapse into the dense clouds that stars require. Jets can cause that. When a jet plows into surrounding material, it can drive shocks through the gas. It can inflate bubbles. It can create turbulence. It can spread energy through the galaxy's atmosphere, heating the gas and keeping it unsettled. In galaxy clusters, these bubbles sometimes appear as cavities in hot X-ray emitting gas, clear signs that something powerful has pushed the material aside. And once the gas is heated, it may no longer cool efficiently. Without cooling, it cannot condense. Without condensation, star formation slows. This is one form of cosmic regulation. A galaxy may look peaceful in starlight, yet deep within, its central engine may be controlling how many stars it will form in the future. In that sense, the galaxy's future can be influenced by an invisible thermostat set near its core. Not every active black hole reveals itself openly. Some are hidden. In many galaxies, thick veils of dust and gas block the central region from view in visible light. From the outside, the galaxy may look ordinary. It may seem calm, balanced, quiet. And yet intense activity may be unfolding behind that curtain. Astronomers uncover these hidden engines by using wavelengths that dust cannot easily block. They also search for signs of heated material and energetic particles. X-rays can pass through layers that would completely obscure an optical telescope. Infrared light can reveal dust that has absorbed energy from a hidden source, then re-emitted it as warmth. And this matters deeply, because it changes our count of active galaxies in the universe. If we looked only with our eyes, or only in visible light, we would miss a large fraction of the story. Hidden black holes remind us that growth can happen behind a curtain, that some of the universe's most dramatic processes are not always on open display. Infrared telescopes are especially helpful here. They reveal dust warmed by stars, glowing softly like cosmic embers. Dust grains may be tiny, but they are powerful storytellers. When young stars blaze inside dusty regions, much of their visible and ultraviolet light is absorbed. The dust warms. And then, like a banked fire, it releases that energy again as infrared radiation. So infrared telescopes can reveal star formation that might otherwise be underestimated or missed entirely. This is especially important in distant galaxies, where intense star formation often happens in dusty environments. By measuring infrared brightness at different wavelengths, astronomers can estimate how much dust is present and how warm it is. That, in turn, offers clues about how intense the hidden star formation may be. Infrared data can also help separate two different sources of power. Sometimes a galaxy glows because stars are forming across large regions. Other times it glows because a compact active nucleus is dominating the energy output. These two processes leave different spectral signatures, so in a sense, infrared astronomy listens for warmth rather than light. It helps us find galaxies building stars behind thick curtains, and it gives us a fuller, more honest picture of how busy the universe has been. Radio telescopes add another layer to the story. They can map cold gas, the raw fuel for making new stars. Stars do not form from just any gas. They form from cold gas, and radio observations are among the best ways to find it. Neutral hydrogen emits a characteristic radio signal. Molecular gas can be traced through molecules such as carbon monoxide, which shines at millimeter wavelengths. These signals show not just how much fuel a galaxy has, but where that fuel is, and how it moves. Astronomers can see gas rotating in a disk. They can see streams flowing inward. They can see disturbed patterns that suggest a recent interaction or a galactic encounter. This is important because starlight alone can hide the supply chain. A galaxy might look faint in visible light, yet still contain a huge reservoir of cold gas waiting to form stars. Radio and millimeter observations turn that hidden reservoir into a map. They help astronomers connect cause to effect. In that sense, star formation is not magic. It is logistics. Cold gas is the inventory, and radio telescopes are how we take stock across the universe. Ultraviolet light tells another part of the story. It highlights hot, young stars. If astronomers want to know where fresh star formation is happening, ultraviolet light is a direct clue. Massive young stars burn hot and shine strongly in ultraviolet wavelengths, but they do so only briefly. They live fast. They fade quickly, or explode. So ultraviolet light acts almost like a freshness indicator. When you see ultraviolet glow, you're seeing recent star formation. Not ancient history, but ultraviolet is delicate information. Dust absorbs it very efficiently. That means a galaxy can be forming many stars and still appear faint in ultraviolet light. So astronomers combine ultraviolet with infrared. The ultraviolet shows what escaped. The infrared shows what was absorbed and then re-emitted. Together, they bracket the truth. Ultraviolet observations also provide clever ways to identify very distant galaxies. As light travels across the universe, intergalactic hydrogen can block ultraviolet light below certain wavelengths. This creates a distinctive drop in brightness. That drop becomes a clue to distance, a fingerprint of remoteness. And with that clue, astronomers can sort the far universe from the near. This is why modern astronomy rarely relies on only one kind of light. A galaxy is not just stars. It is stars, gas, dust, magnetic fields, and sometimes an active black hole, all layered together. No single wavelength can show all of that at once. Visible light reveals starlight and structure. Infrared reveals hidden star formation and warm dust. Radio and millimeter observations trace cold gas and energetic particles. X-rays reveal hot gas and extreme conditions. When astronomers combine all of these views, they can build a fuller narrative. They can see where the fuel is, where stars are forming, how energy is moving, and whether a central engine is shaping the life of the galaxy. That is why the same galaxy can look peaceful in one band and wild in another. Multi-wavelength astronomy also protects against simple mistakes. A bright galaxy may be glowing because it is forming stars, or it may be glowing because a compact active nucleus is dominating the light. And that difference matters, because it changes how we understand the history of the universe. In the end, the story of a galaxy is like a layered song. Each wavelength carries a different part of the melody. And then there is redshift, a subtle clue written directly into light itself. Redshift is often described as a cosmic speedometer. When a distant galaxy is moving away from us as space expands, its light is stretched toward redder wavelengths. Astronomers measure this by spreading the light into a spectrum, then looking for familiar fingerprints left by atoms such as hydrogen. Those fingerprints do not disappear. They shift. They appear slightly displaced from where they would be if the source were nearby and still. And the amount of that displacement tells astronomers how strongly expansion has stretched the light during its journey. It is a little like hearing a siren drop in pitch as it moves away. Except here, the effect is written not in sound, but in color. With redshift, a galaxy becomes more than a faint patch of light. It becomes a marker in a much larger pattern, a data point in the expansion of the universe itself. Measure enough galaxies, and you can watch the universe swell over time. And that is one of the quiet wonders of astronomy. Distance, motion, and history, all encoded in a single shift of light. Greater redshift usually means greater distance and an earlier moment in cosmic time. Because light takes time to travel, a very distant galaxy is never a present-day view. It is an old view, a message from long ago. Redshift helps astronomers place those messages into order. The greater the redshift, the more the light has usually been stretched by the expansion of space. And the more it has been stretched, the longer it has usually been traveling. That allows astronomers to arrange galaxies by era, to place them into a kind of cosmic sequence. Young-looking, irregular systems can be set beside later, more settled ones. And from that comparison, a quiet question begins to emerge. What changed? When was star formation at its most active? When did galaxies begin to look more like the familiar shapes we see nearby today? There are small complications, of course. Local motions can add little wrinkles to the pattern, but the overall trend remains powerful. It turns the sky into a layered archive. So when we look farther into space, we are also looking farther into time, deeper into the early building years of galaxies and of the universe itself. There is another idea here that sounds strange at first. The expansion of space can carry galaxies away faster than light, without breaking physics. That sounds impossible, as though a rule has been broken, but it is a different kind of motion. Special relativity limits how fast objects can move through space. Cosmic expansion is different. It is space itself stretching. And when space stretches across vast enough distances, the separation between faraway galaxies can increase at an effective rate greater than the speed of light. No galaxy is racing past a light beam in its own local neighborhood. Instead, the fabric between distant neighborhoods is growing, stretching, lengthening. That is why there are regions of the universe we could never reach, even with a perfect spacecraft. And it is also why some galaxies are visible only because their light began traveling when they were closer to us. In a smaller universe, over time, expansion can turn the reachable into the unreachable, the visible into the forever beyond. It is an unsettling thought, but also a beautiful one. It means the universe has a moving horizon. Its limits are shaped not by walls, but by growth. And this leads to one of the gentlest truths in astronomy. We never see a galaxy as it is now. We only see it as it was when its light left. Every telescope is a kind of time machine, not because it bends time, but because light needs time to travel. Every image is a delayed message. For a nearby galaxy, the delay is still enormous compared with a human life. For a distant galaxy, the delay reaches into the deep past, so the universe presents itself to us as a mixture of eras all at once. In one survey of the sky, astronomers can see a relatively mature galaxy nearby, and in the same frame, a galaxy from a far younger age of the cosmos. This is not a trick of interpretation. It is simply the consequence of the finite speed of light. Astronomers embrace that fact. They build timelines from distance. They compare galaxy populations across redshift. They search for trends. They look for turning points, moments when galaxy growth changed pace. And the result is humbling. The present is not what the sky shows us. What we see is a vast collection of past moments, all arriving together in a single night. Some galaxies may no longer exist in the form we observe, even though their light still reaches us. A photon does not update itself. Once it leaves a galaxy, it carries only the story of that moment. Nothing more. Over billions of years, that galaxy may merge, transform, or be torn apart. But the traveling light does not know that. So it is possible to observe a galaxy as it once was, even if its later fate has already unfolded. This creates a strange and beautiful kind of cosmic delay. The sky contains true historical records, scenes from long ago, objects that may have changed beyond recognition since their light first departed. Astronomers keep this in mind when they reconstruct cosmic evolution. They do not assume a distant galaxy is still in the same state today. They treat it as an ancient snapshot. Then they place it among many other snapshots from different distances, and therefore from different times. It is a little like receiving postcards mailed across ages, each one stamped with the moment it began its journey. And that journey can be almost impossible to imagine. A single particle of light may leave a distant galaxy, then spend most of the universe's history traveling, crossing expanding space, passing between galaxies, wandering across billions of years, and then, finally, it reaches Earth. It meets a telescope, and that last encounter is over in an instant. Billions of years of travel, gathered into one quiet click of a detector. That contrast is part of what makes astronomy feel so magical, while remaining completely physical. A deep observation is really an act of patience, a careful collecting of rare arrivals. One photon is only a whisper, but many photons become a spectrum, a shape, a story, and each one is proof that the universe, though vast, is not completely closed. Space has remained transparent enough for messages to cross cosmic distances. So when you look at a faint galaxy, you're participating in an exchange that began long before humans existed and ends in a small, quiet moment at a telescope. And once that light arrives, astronomers can learn even more from it. A galaxy's spectrum can reveal its elements like a barcode written in light. When starlight is spread out into a rainbow, certain dark gaps and bright features appear at specific wavelengths. These patterns happen because atoms and molecules absorb or emit light in precise ways. Hydrogen has its own signature. Oxygen has its own. So do carbon, nitrogen, and many others. By reading those patterns, astronomers can infer what a galaxy is made of, even when it is far too distant for individual stars to be seen. And the spectrum carries more than chemistry. It can also reveal temperature, density, motion. The lines can broaden. They can shift. And those changes tell us that gas is moving, or that physical conditions inside the galaxy are changing. This is why spectroscopy is one of astronomy's most powerful tools. It turns faint light into a report, a chemical description, a physical record. It transforms a dim smudge into a place with measurable properties. There is something deeply practical in that wonder. You can learn what exists in a galaxy simply by studying the light that reaches you. No visit required, no touch required, only patience and attention. And when astronomers look at early galaxies, they find something important. Those galaxies contained fewer heavy elements. That is because stars had less time to make them. In the early universe, most matter was hydrogen and helium. Only tiny amounts of heavier elements were present. The richer materials needed for rocky planets, for complex chemistry, for the ingredients of later worlds, had to be built inside stars. And that process takes time. A star must live. It must fuse light elements into heavier ones, and then it must return that material to space, through winds or through explosions. Early galaxies had hosted fewer generations of stars, so their gas was less enriched. Astronomers can see this in their spectra. Certain heavy element lines appear weaker, and the gas itself behaves differently. Gas with fewer heavy elements cools in different ways. It fragments differently, and that can influence what kinds of stars form. This is why early galaxies were not simply younger versions of modern galaxies. Their materials were different. Their toolkit was simpler. And that difference shaped how quickly they could build dust, structure, and future star systems. The first generations of stars changed all of that. Those early stars were pioneers in a chemically simple universe. As they aged, they forged heavier elements in their cores. Then, when they shed their outer layers or exploded, they seeded their surroundings with those new materials. That enrichment changed what galaxies could do next. Heavier elements help gas cool more efficiently. Cooler gas can collapse into denser clouds. Those clouds can form new stars more easily, and they can also form dust grains, which reshape a galaxy's light and chemistry even further. Enrichment also created the raw material for future planets, for minerals, for molecules, for more complex structures. So astronomers search for this transition across cosmic time. They ask when heavy element content began to rise, how quickly it spread, and how that change affected galaxy growth. Because the change is not only about composition, it is about capability. With each new stellar generation, a galaxy becomes more chemically rich and more structurally complex. The first stars were not only bright, they were architects. They rewrote their galaxies from the inside out, and sometimes that rewriting happened violently. Supernovae can drive gas outward and regulate how quickly a small galaxy grows. In a small galaxy, gravity has a lighter grip. That makes the system more vulnerable to powerful events. When a massive star ends its life as a supernova, it releases an enormous amount of energy into the surrounding gas. The blast can heat that gas, stir it, push it outward, and in some cases, eject it from the galaxy altogether. If enough gas is lost, star formation slows. The fuel supply has been reduced, and if the gas is not fully expelled but only heated, it may still take a long time to cool down again. Only after cooling can it settle back into dense clouds, where new stars may finally form. So even destruction becomes part of the rhythm. A star lives. A star enriches. A star explodes. And in doing so, it shapes what the galaxy can become next. Either way, growth becomes uneven, not smooth and steady, but stop and start. A galaxy may pass through active periods, then settle into quieter ones. Then, after time, another burst may begin. This kind of feedback helps explain why some dwarf galaxies form stars in short episodes, separated by long, calmer stretches. It also changes their chemistry. When gas flows outward, it can carry freshly made elements away, before those new materials have time to mix fully through the galaxy. So a supernova does more than end a star's life. It helps regulate the life of the galaxy itself. In that sense, supernova feedback is a kind of galactic self-control. It keeps small galaxies from turning all of their gas into stars too quickly, and it helps set the pace of their long, irregular, uneven lives. Some galaxies, though, enter a much more dramatic phase. They undergo what astronomers call a starburst. For a brief stretch of cosmic time, a galaxy can seem to press down on an accelerator. Gas that might otherwise have formed stars slowly, over millions of years, is pushed into dense pockets. And those pockets suddenly ignite with new star clusters. In nearby examples, starburst regions can be crowded with massive, short-lived stars. These stars shine intensely. Their radiation floods the surrounding gas. Their winds reshape their environment. And in more distant galaxies, the effect can become even more striking. A galaxy in starburst may glow brilliantly in infrared light because dust absorbs so much starlight, then releases that energy again as heat. But starbursts do not last long, not on a galactic clock. They burn through fuel. They stir the gas. They drive winds. They end in explosions. And that is part of what makes them so valuable to study. Catching a starburst is a little like catching a thunderstorm. You see what a galaxy can do at its most intense, and you also begin to understand what prevents it from living that way forever. Very often, starbursts follow collisions. When two galaxies pass near one another, gravity does more than tug on their stars. It disturbs their gas. It twists it. It removes some of its angular momentum and pushes it inward. As streams of gas converge, they collide. They shock. The pressure rises quickly, and that squeeze can turn large, diffuse reservoirs into dense, star-forming clouds. In some mergers, Bright knots appear where tidal forces pile gas into overlap regions. Those knots can become nurseries for enormous star clusters. Collisions also scramble orbital paths. Gas that once moved in relatively orderly patterns begins crossing over itself, and that chaos can become productive. It increases the chance of cloud collisions. It can trigger waves of star formation that move through the system, but eventually, the same violence that helped start the burst can help end it. Feedback heats the remaining gas, it disperses it, and the burst begins to fade. A merger is both a spark and a stopwatch. Some distant galaxies also host vast glowing nebulae. Around certain galaxies, especially in the early universe, this glow stretches far beyond the main body of starlight. That light often comes from gas being lit up by young, massive stars, or by energetic activity near the galaxy's center. The nebula becomes a kind of lantern shade. It reveals where gas is located, and sometimes how it is moving. Astronomers look for specific emission lines, especially from excited hydrogen. Then they map how those lines shift across the glowing gas. From that, they can infer motion. Sometimes the glow outlines outflows, gas streaming away from the galaxy. Sometimes it traces inflowing material, feeding future star formation. These extended nebulae make galaxies feel less like isolated islands and more like living systems with atmospheres. The stars form the bright center, but the surrounding gas is the active boundary, the place where growth and change are negotiated. Some galaxies do something even more important. They leak ultraviolet light, and in doing so, they may have helped transform the early universe. In the earliest epochs, the space between galaxies contained a great deal of neutral hydrogen. That neutral hydrogen is very good at absorbing ultraviolet light. So for the universe to become more transparent, enough energetic photons had to escape from galaxies and reach the gas between them. Not every galaxy could do that. Ultraviolet photons are easily trapped. Dust can absorb them. Dense hydrogen clouds inside a galaxy can block them. Escape becomes easier only when winds from stars and explosions from supernovae carve channels through the gas, or when star formation happens near the edges of a galaxy, where less material stands in the way. Astronomers search for these leaky galaxies by looking for spectral signs that ultraviolet light is getting out. And when they find good candidates, they are finding more than curiosities. They are finding possible agents of a major cosmic transition, a time when the fog of neutral hydrogen began to clear across the universe. That transition is called reionization. It marked the end of the cosmic dark ages, and it made space more transparent to light. After the Big Bang cooled enough for electrons and protons to combine, much of the universe became neutral. That neutral gas absorbed energetic light very efficiently. For a time, the first luminous objects had not yet fully transformed their surroundings, but slowly. Early stars and galaxies produced ultraviolet radiation. That radiation broke hydrogen back into ions, and this change spread outward in growing bubbles. More stars formed. More galaxies lit up. More bubbles expanded. Eventually, those bubbles overlapped, until most of the hydrogen between galaxies became ionized again. Once that happened, ultraviolet light could travel more freely. The universe became a clearer place to look through. Reionization is not just a label for a chapter in history. It changed what kinds of galaxies could form, because ionized gas behaves differently from neutral gas. Astronomers reconstructed this era by combining evidence from distant galaxies, from bright background beacons, and from the cosmic microwave background. It was one of the universe's great phase changes. Like dawn, arriving across all of space. There is another gentle way astronomers study the universe between galaxies. They look at hydrogen absorption lines. Even when intergalactic gas is too thin to glow on its own, it can still make itself known. It can steal certain wavelengths from background light. When light from a distant source passes through hydrogen, it loses intensity at characteristic wavelengths. That leaves behind a series of absorption features. By measuring where those features appear, astronomers can infer the gas along the line of sight, its motion, its distance, its distribution. This technique is often used with bright quasars. Sometimes galaxies can serve as background lamps too. And the pattern is not just one shadow. It is a layered set of imprints left by many clouds at many distances. A single line of sight becomes a probe of the cosmic environment. It is a way of seeing what does not shine. The universe becomes readable not only by what it emits, but by what it blocks. In that sense, intergalactic gas records structure like mist revealing a hidden landscape. The gas between galaxies tends to collect in the same broad patterns that galaxies do, because both respond to gravity, so those absorption features can trace filaments, nodes, diffuse regions, places that are otherwise difficult to map. And with enough background sources, astronomers can do something like tomography. They combine many sightlines and slowly reconstruct a three-dimensional picture of matter across part of the sky. This approach is still developing, but it is one of the most exciting ways to connect galaxies to their feeding grounds, because that gas is not just scenery. It is the reservoir that may supply future star formation. It is also the medium that carries heavy elements outward through galactic winds. Once you treat intergalactic gas as a record, new questions become possible. Where does a galaxy's next fuel come from? Where do its outflows go? The answers live in the faint, structured mist between the bright islands. Over time, another change often appears. A galaxy's metallicity tends to rise. In astronomy, metals means all elements heavier than helium. And as a galaxy ages, those elements usually become more abundant. Each cycle of star formation takes gas, builds heavier atoms through fusion, and later returns some of that enriched material through stellar winds and stellar deaths. Over long stretches of time, this tends to increase the abundance of elements such as oxygen and carbon in the gas that will form the next generation of stars. Astronomers measure metallicity in distant galaxies by studying emission lines from glowing gas in star-forming regions. They compare ratios of lines that depend on composition and temperature. And when they do this across cosmic time, a broad trend appears. Earlier eras usually show lower metallicities. Later eras tend to show higher ones. But the details matter. The rise is not uniform. It depends on how efficiently a galaxy turns gas into stars, how much fresh gas flows inward, and how much enriched gas flows outward. So metallicity becomes a kind of diary, a record of a galaxy's past choices. Small galaxies, in particular, can lose metals easily. Their gravity is gentle, and in a low-mass galaxy, escape is easier. That matters because the same events that create heavy elements also inject energy into the surrounding gas. When massive stars explode or drive strong winds, the hot, metal-rich material can be launched outward in a galactic wind. And if the galaxy's gravitational pull is weak enough, some of that enriched gas can leave for good, drifting away into the intergalactic medium. So even the elements a galaxy works hard to create may not always stay home. This helps explain something curious about many small galaxies. Many dwarf galaxies remain chemically simple, even after experiencing several periods of star formation. At first, that may seem surprising. After all, they have made stars, and stars create heavier elements. But the real question is not only how much a galaxy produces, it is also how much it manages to keep. Astronomers study this by comparing metallicity, the amount of heavy elements, with the mass of a galaxy. They also search for signs of gas flowing outward in the spectra of distant systems, and gradually a clear picture begins to appear. Small galaxies can be unexpectedly generous. They release newly forged elements into the surrounding universe, even while struggling to enrich themselves. Larger galaxies, however, behave differently. Massive galaxies are much better at holding on to enriched gas, and because of that, they can build heavier elements more steadily over time. You might imagine gravity in a large galaxy like a deep bowl. Energetic events can throw hot gas upward. Supernova explosions, stellar winds, violent bursts of radiation. But much of that material cannot escape the bowl entirely. Instead, it rises, slows, and eventually cools. And then it falls back inward again. Astronomers sometimes describe this process as a galactic fountain. Material is lifted up, and then gently rains back down. Because of that recycling, enriched gas is not lost. It is reused. And in many massive galaxies, there is another layer of protection. A large halo of hot gas surrounds the galaxy. This halo traps outflowing material and mixes it slowly over time. The result is a steady buildup of heavy elements, especially in regions where star formation continues for billions of years. Astronomers see hints of this steady pattern when they compare metallicity with galaxy mass. They also see it in the way metal-rich gas spreads across galactic disks. But even this story is not perfectly simple. Large galaxies do not keep everything. They still launch winds. They still exchange matter with their surroundings. The real difference is balance. Their stronger gravity simply makes it harder for valuable material to escape forever. And that balance helps them build richer chemistry over cosmic time. Some galaxies appear calm, quiet, even inactive. Astronomers sometimes describe them as red and dead. Yet even these galaxies can continue growing. They grow not by forming new stars, but by swallowing smaller galaxies. A galaxy can stop creating fresh stars and still gain mass. In many large reddish galaxies, growth happens through what astronomers call dry mergers. These are mergers with very little cold gas. So instead of triggering bright new waves of star formation, the incoming galaxy mostly contributes the stars it already contains. Over time, those added stars spread outward. They build a wide, faint outer envelope, and the galaxy becomes larger, without becoming bluer. Astronomers detect this quiet growth by measuring how galaxy sizes change across cosmic time. They also find faint stellar shells and subtle gradients of stars that reveal past mergers. It is a very different style of evolution. The central light of the galaxy may appear calm and ancient, but far from the center, the outskirts slowly thicken, layer by layer, almost like the rings of a tree. This gradual accumulation helps explain why some giant galaxies are so enormous today. Their growth did not require constant star formation. It required patience, gravity, and many small arrivals. In fact, astronomers sometimes call this process galaxy cannibalism. It sounds dramatic, but in reality, it is very slow. When a large galaxy captures a smaller one, the process can take a very long time. The smaller galaxy begins orbiting its larger neighbor. With each orbit, it loses energy. Tidal forces begin to stretch it. Stars are stripped away from its outer edges first, then from deeper and deeper regions. Eventually, the original galaxy dissolves completely, spreading into faint streams of stars. Those streams become part of a delicate halo surrounding the larger galaxy. These halos are difficult to see, but deep images reveal them as arcs, shells, and faint ribbons of starlight. Each structure tells part of the story. The shape of the stream reveals the path the smaller galaxy once followed. The chemistry of the stars reveals where they originally formed. Captured dwarf galaxies often carry distinctive chemical signatures, and that allows astronomers to identify them long after they have dissolved. In this way, the outer regions of a galaxy become something like a cosmic scrapbook. The bright central galaxy is the main story, but the halo is the margin filled with notes, annotations, and memories of past encounters. Galaxy cannibalism is not a single bite. It is a long, slow meal, one that reshapes both the appearance and the history of the galaxy. Inside many spiral galaxies, another structure quietly grows. At the center sits a rounded region called the bulge. It looks different from the thin, flat disk of the galaxy. One way this bulge forms is through the scrambling of stellar motion. Encounters with other galaxies, internal instabilities, and smaller mergers can shake a disk. Some stars are knocked out of their orderly circular paths. Instead of orbiting neatly in a plane, they begin moving in many directions. The central region thickens, and slowly, a bulge appears. This process is less like stacking new stars and more like stirring the ones that already exist. Astronomers study bulges by measuring how stars move. They also compare bulge properties with the rest of the galaxy. Some bulges look ancient and classical, as though they formed during violent early events. Others seem to grow slowly through gentle internal changes. Either way, the bulge keeps a record. It tells us how stable the disk has been and how often it has been disturbed. Another quiet architect can appear inside spiral galaxies: a bar. A bar is a long, bright structure of stars that stretches across the center of a galaxy. At first glance, it may seem decorative, but it can play an important role. The bar's gravity pulls on the gas in the disk, slowly, gently. It nudges that gas inward. Over time, the gas drifts toward the center. There it collects into dense rings, or reservoirs near the galaxy's core. And those reservoirs can ignite new star formation. So while the outer disk forms stars slowly, the central region may suddenly become active. Bars themselves are not permanent. They can strengthen, weaken, or even dissolve, depending on how mass moves through the galaxy. Astronomers study bars by mapping gas flows and comparing star formation in galaxies with and without bars. In many ways, a bar acts like a quiet architect. It rearranges a galaxy's fuel supply without needing a dramatic collision. And over billions of years, it can rewrite the central story of the galaxy. Sometimes galaxies display another remarkable pattern: a ring. Galactic rings can form after collisions, like ripples spreading across a cosmic pond. When a smaller galaxy plunges through the disk of a larger one, a wave travels outward through the stars and gas. As that wave moves, it compresses material. Where the gas becomes compressed, star formation ignites. The result can be a brilliant circular ring of young stars. These rings slowly expand outward over time, They are not permanent decorations. They are moving consequences of an encounter. Astronomers can estimate the age of a ring by measuring its size and the ages of the stars inside it. They can even simulate the collision that created it, reconstructing the path of the intruding galaxy. In this way, the ring becomes a visible memory, a graceful reminder of a moment long past. Another unusual structure appears in polar ring galaxies. In these systems, a ring of stars and gas orbits almost perpendicular to the main disk. It can look as though one galaxy is wearing another galaxy like a belt. This strange arrangement usually signals a complicated past. Perhaps the galaxy captured gas from a passing neighbor, or perhaps a smaller galaxy was torn apart, its material settling into a tilted orbit. Because the ring sits at such an unusual angle, it becomes a sensitive probe of the galaxy's gravitational shape. If the hidden mass around the galaxy is slightly uneven, the ring's orbit will respond. That makes polar ring galaxies valuable laboratories for studying how mass is distributed beyond visible stars. Astronomers observe these systems in many wavelengths. They track young stars forming in the ring and older stars in the host galaxy. So a single galaxy ends up carrying two orbital stories at once. It becomes a living diagram of how galaxies acquire material from outside themselves. And finally, not every galaxy shows the dramatic spiral patterns we often imagine. Some disk galaxies have almost no spiral arms at all. They appear smooth, quiet, featureless. Their light spreads evenly across the disk, and their stars are mostly old. These galaxies offer another quiet lesson. Spiral arms are not permanent structures. They are patterns, shaped by rotation, mass distribution, and the presence of gas. If a galaxy contains little cold gas, or if its disk has been dynamically heated so stars move more randomly, those patterns can fade. Environment can also play a role. In crowded galaxy clusters, gas can be stripped away. Without that gas, bright star-forming arms cannot easily appear. Astronomers study these smooth disks by measuring their rotation and by mapping how the ages of stars change from center to edge. In a sense, these galaxies can look like systems in retirement. They still rotate. They still shine. But the dramatic patterns across their disks have faded, and even that absence tells a story. Because the lack of spiral arms is not emptiness, it is information, a quiet record of fuel, stability, and the long history of interactions that shaped the galaxy we see today. Irregular galaxies can look untidy at first, almost accidental, like starlight spilled across the dark, without the graceful symmetry of a spiral, and without the quiet balance of an elliptical galaxy. But that apparent disorder often carries a very precise history. The mess is not meaningless, it is evidence. An irregular galaxy may have been stretched by tidal forces. It may have passed through a recent burst of star formation. It may have grown through uneven flows of gas. And because many irregular galaxies are small, their gravity is weaker. Their structure is easier to disturb. So even modest events can leave deep marks. Astronomers study these galaxies carefully. They look at where young stars are clustered. They trace where gas is most concentrated. They measure how different parts of the galaxy move relative to one another. And slowly, a story begins to appear. Sometimes the brightest region is not in the center. Sometimes the gas disk is twisted or offset. Sometimes one side of the galaxy seems more active than the other. These are gentle clues that something happened, even if it happened long ago. Irregular galaxies matter for another reason too. They resemble the kinds of galaxies that were more common in the early universe. So when astronomers study nearby irregular systems, they are, in a way, studying living examples of youthful galactic behavior. Their chaos is not a failure of form. It is a readable signature. And sometimes that signature stretches outward into something even more dramatic. Long, thin streams of stars can be pulled from galaxies during close encounters. These are called tidal tails. When two galaxies pass near one another, gravity can tug on their outer stars and gas, stretching them like soft taffy. The result can be enormous arcs of light that extend far beyond the main bodies of the galaxies. These tails are not just beautiful, they are revealing. They show that galaxies are not rigid fixed objects. Their outer regions are loosely bound. They can be reshaped, pulled, stretched, rearranged, and tidal tails can do more than record a past encounter. They can also guide gas into new places. They can channel material outward. Sometimes they even trigger new star formation along the tail itself. Astronomers use the shapes and lengths of tidal tails to reconstruct the encounter that made them. How close did the galaxies pass? How were they oriented? Which direction did the forces pull? In some systems, two separate tails point away in different directions, each one tracing a different gravitational response. With time, some tails fall back inward. Some disperse. Some remain as faint structures in the outskirts of galaxies. But whatever their fate, they remind us that galaxies evolve through interaction, and that gravity, despite its power, can sculpt with extraordinary delicacy. Sometimes those tails create something new. In a few tidal tails, clumps of gas and stars become dense enough to collapse into self-bound objects. These are often called tidal dwarf galaxies. Unlike many dwarf galaxies, which formed long ago inside their own dark matter halos, tidal dwarfs are made from recycled material, pulled out of larger galaxies during an encounter. That gives them a distinct character. They can contain relatively large amounts of heavy elements for such small systems, because the gas they formed from was already enriched inside a bigger galaxy. Astronomers search for these newborn dwarfs by looking for bright knots inside tidal tails. Then they measure the motions of those knots to see whether they are truly gravitationally bound, or only temporary condensations. It is a remarkable kind of second-generation creation. A collision can tear galaxies apart, and at the same time create new structures from the debris, like sparks thrown from a grinding wheel. It is a reminder that galactic evolution is not only about destruction, it is also about recycling, about reshaping, about small new systems emerging from the remains of larger ones. Our understanding of these distant worlds changed dramatically when astronomers began looking deeper into apparently empty regions of sky. In the 1990s, the Hubble Space Telescope was pointed at a tiny patch of sky that seemed almost blank. It was a bold decision. Telescope time is precious, and the chosen region looked, at first glance, unremarkable. But after days of exposure, the image returned full of galaxies. Not a few, not scattered here and there, but everywhere. That image became known as the Hubble Deep Field, and it changed more than astronomy. It changed intuition. It showed that even a dark-looking patch of sky is likely full of distant galaxies. It made the universe feel less like a sparse scattering of islands, and more like a vast populated ocean. It also offered something powerful to astronomers. The same image contained nearby galaxies and extremely distant ones together. So a single frame became a layered record of cosmic history. The deep field became a cultural turning point as well. a reminder that the universe rewards patience, and that sometimes, if you simply keep looking long enough, emptiness becomes abundance. Later, astronomers pushed that same idea even further. They created the ultra-deep field. This was the same basic approach, but taken to a greater extreme. By collecting light for much longer, astronomers reached galaxies so faint they had once been invisible. And that matters, because faint often means far, and far often means early. The ultra-deep field became a deeper archive of the young universe. It was filled with small reddish smudges, subtle hints of distance and youth, and it taught another practical lesson. Many secrets in astronomy are not hidden by complexity. They are hidden by faintness. If you collect light patiently enough, the universe slowly hands over photons that were arriving all along. The ultra-deep field also helped astronomers in another way. It gave them better statistics. Instead of relying only on a few bright, unusual galaxies from the early universe, they could include more ordinary ones too. And so the picture of the young cosmos became richer, messier, more realistic. Then came another great leap: the James Webb Space Telescope. Webb was designed for a universe in which the oldest light has been stretched out of visible wavelengths and into infrared. That is where ancient starlight now arrives, and Webb is exquisitely sensitive there. This means it can detect galaxies that are both very distant and intrinsically faint. Galaxies whose visible light might be weakened by distance or hidden behind dust. Webb also carries instruments that can analyze spectra, reading chemical fingerprints from very early times, so those tiny patches of light stop being anonymous dots. They become places. Places with gas, with stars, with motion, with measurable properties. Some early galaxies seen by Webb appear compact and intense. Others look more extended and more structured, earlier than many astronomers expected. Each new observation feeds back into our models of galaxy formation. Webb does not simply let us see farther. It changes the questions we dare to ask. Infrared light is especially important because it helps overcome two great obstacles in astronomy: dust and distance. Dust is excellent at hiding galaxies in visible light, and distance weakens everything. Infrared can help with both problems. Longer wavelengths pass through dusty regions more easily, and they also match the red-shifted glow of old distant stars. So with Webb, astronomers can find galaxies that were previously undercounted, not because they were absent, but because they were disguised. This matters for cosmic bookkeeping. If dusty star-forming galaxies are missed, then the universe may appear to have built its stars more slowly than it really did. Infrared observations also help separate different components inside galaxies. Dust heated by star formation leaves one kind of infrared signature. Older stars leave another. That separation helps astronomers understand what is actually producing the light we receive. In a way, infrared astronomy is a kind of honesty test. It checks whether a galaxy is truly quiet or simply active behind curtains that older instruments could not see through. Some of Webb's observations have raised especially intriguing questions. A few early galaxies seem larger, or more substantial, than expected. And when that happens, astronomers pause carefully. Are these galaxies truly bigger than models predicted so early in cosmic history? Or do they only appear large because of how their light is distributed? Could subtle lensing be magnifying them? Could the measurements be more difficult than they first appear? These questions matter because galaxy growth is tied closely to dark matter, gas inflow, and the efficiency of star formation. A single surprising population can hint at missing physics, or it can reveal just how hard it is to measure faint, distant objects accurately. So astronomers respond with care. They cross-check sizes. They refine redshifts. They compare masses using multiple methods. They look for consistent patterns across different parts of the sky. And the debate itself is valuable. The early universe is a hard testing ground for theory. If large galaxies really did form quickly, then nature may be even more efficient at building structure than we once thought. When a result looks especially strange, astronomers do not simply accept it or dismiss it. They test every step. They re-examine the distance estimates. They revisit the spectra. They account for lensing by faint foreground mass. They check the assumptions used to estimate stellar mass, including how stars form, how bright they should be at different ages, and how much dust may be dimming them. They gather deeper spectra. They compare independent instruments. They run simulations to model what the telescope should see. They even revisit calibration details. Because near the limits of detection, a small bias can grow into a large misunderstanding. This careful work is not retreat. It is the engine of progress. Either the surprising galaxies become less surprising, or the evidence grows stronger until theory must adapt. In either case, our picture of the universe becomes sharper, more trustworthy, more real. And this leads to one of the most satisfying developments in astronomy. A faint galaxy may first appear as nothing more than a tiny, unresolved point, just a dot. But with better instruments, greater sensitivity, and finer resolution, that dot can become a shape, and the shape can become a story. You might see a stretched arc, hinting at gravitational lensing. You might see a compact, bright core surrounded by diffuse light, suggesting different stellar populations. You might see multiple clumps, signs of a turbulent stage of assembly. Then spectroscopy adds another layer. Now the galaxy is not only a shape, it has motion. Its gas may be rotating, or flowing outward, or separating into different components. And this gradual transformation, from a faint point of light to a measured galaxy with structure, chemistry, and history, is one of the most satisfying arcs in all of astronomy. The object itself does not change. What changes is our ability to question it. Our tools improve. Our images grow sharper. Our measurements become deeper. And with each new advance, something beautiful happens. Mystery becomes measurement. And then, measurement opens the door to a new kind of mystery. That process teaches something quiet and important. Patience. Many galaxies that once seemed simple, or vague, or almost featureless, become far more interesting when the data improves. A faint dot is often not just a dot. It is a galaxy waiting for better questions and better instruments. One of the most patient things astronomers do is take long exposures. A long exposure is a little like filling a cup one drop at a time. For very distant galaxies, photons arrive rarely. And when they do arrive, they are mixed with background light and with noise from the detector itself. So deep observing becomes an act of accumulation. The longer you wait, the more true signal you gather. The galaxy slowly begins to emerge. Its light strengthens faster than the noise. Shape begins to separate from static. Astronomers often do not take just one long image. Instead, they take many shorter images and combine them. They stack them carefully. That helps remove cosmic ray hits and other unwanted artifacts. So the final image may look sudden and complete, but it was built slowly, patiently, carefully, and long exposures demand steadiness. The telescope must point with great precision. The calibration must remain consistent. If either one drifts, the faint signal can smear away. But when everything holds steady, the reward is remarkable. Galaxies that would otherwise remain invisible begin to appear. Low surface brightness systems, extremely distant systems, populations that sit right at the edge of detectability. This is why deep fields matter so much. They show us what the universe looks like when we stop glancing and start listening. The photons were always coming. We simply had to remain long enough to receive them. Space telescopes help with this in another important way. They do not have to look through Earth's atmosphere. And that matters. Our atmosphere is a wonderful shield for life. But for astronomy, it is a restless lens. Air turbulence makes starlight wobble. That wobble spreads a faint object's light over more pixels and lowers its contrast. From orbit, a telescope escapes that blur. The background becomes steadier. The image becomes sharper. And sharpness is not only about beauty. It helps astronomers tell a distant galaxy from a nearby star. It helps separate small galaxies that would otherwise blend together. It allows better measurements of size, shape, and structure. And those details become especially important when comparing galaxies across cosmic time. Space telescopes also open windows onto wavelengths that Earth's atmosphere blocks or absorbs. Much of the ultraviolet, parts of the infrared. That means astronomers can study young hot stars, warm dust, and other features that ground-based telescopes may not access as easily. Above the air, the sky grows quieter, and faint galaxies become easier to hear. But Earth-based astronomy has learned to answer the atmosphere in clever ways. One of those answers is adaptive optics. Adaptive optics is a smart response to a stubborn problem. If the air is distorting incoming light, then perhaps the distortion can be measured. And if it can be measured, perhaps it can be corrected. That is exactly what adaptive optics tries to do. The system watches a reference source, sometimes a real star, sometimes an artificial laser guide star. Then, in real time, it adjusts a deformable mirror, hundreds of times each second. Tiny corrections. Again and again. The result can approach the clarity of space-based observations, especially in infrared light. For distant galaxies, this can reveal fine detail from the ground, compact cores, small clumps, close galaxy pairs that would otherwise blur together. It also improves spectroscopy. Instead of averaging all the light into one broad signal, astronomers can begin to map motion across a galaxy. They can see whether gas is rotating, or flowing outward, or gathering into separate components. Adaptive optics does not replace space telescopes. It works alongside them. Ground-based observatories can be enormous. They can hold instruments too large or complex to send into orbit. So together, ground and space form a partnership. Space provides stability and darkness. The ground provides size and flexibility. And technology steadily softens the atmosphere's interference. As these tools improve, astronomers do more than study individual galaxies. They begin to map the universe itself. A sky full of points becomes something deeper. Once distance is added, that is what large galaxy surveys do. They measure where galaxies appear on the sky. Then they estimate how far away each one is, often using redshift. And suddenly, the result is no longer a flat chart. It becomes a volume, a three-dimensional slice of the cosmos. When those maps are visualized, something extraordinary appears. Filaments, knots, voids, dense regions and quiet ones, a structure that would remain hidden in a simple photograph. These surveys also show that different kinds of galaxies prefer different neighborhoods. Bright, massive galaxies tend to gather in denser regions. Smaller galaxies are more widely scattered. And with each new survey, the census grows. The pattern sharpens. Abstract ideas about the large-scale structure of the universe begin to feel almost navigable. It is one of astronomy's great acts of imagination made real. We take faint, distant smudges and place them into an architecture that spans billions of light years. And once that map exists, it becomes more than a map. It becomes a measurement of how the universe behaves. Because structure should grow over time. Gravity tries to pull matter together. Cosmic expansion works against that pull. And dark energy appears to make the expansion speed up. The balance between these effects leaves fingerprints in the distribution of galaxies. How clumpy are they? How strongly do they cluster? How does that change with distance, and therefore with time? By measuring clustering across cosmic history, astronomers test whether the universe grew structure at the rate our best models predict. And small differences matter, because small differences may hint at new physics. These maps are also checked against other kinds of evidence. So the story is not built on just one method. In the end, a galaxy survey becomes more than a catalog. It becomes a test, a way of asking whether gravity, expansion, and dark energy have behaved as expected, or whether something subtle is still missing. One especially elegant clue comes from something called baryon acoustic oscillations. The name sounds technical, but the idea is surprisingly poetic. In the early universe, ordinary matter and light were tied together in a hot plasma, and in that plasma, sound waves could travel. They pushed matter outward in expanding shells. Later, when the universe cooled enough for light to break free, those waves froze into place, and they left behind a faint preference for a certain separation scale in matter. Billions of years later, that preference still remains, not as a visible pattern to the eye, but as a subtle statistical feature in how often galaxies are separated by a certain distance. It takes huge surveys to detect, but once it is measured, it becomes incredibly useful. Because it comes from early universe physics we understand well. This is one of the most lovely ideas in cosmology. A sound wave from the infant universe left behind a quiet imprint. And modern galaxy maps can still find it. Not with ears, but with statistics. A silent echo written across the sky. That spacing acts like a cosmic ruler. Because the preferred scale is known, astronomers can use it as a standard of length. If the ruler appears stretched or compressed at different redshifts, then it reveals how the universe expanded between then and now. So surveys measure that scale again and again, across cosmic time. And from that, astronomers reconstruct the expansion history of the universe. This method is powerful because it is geometric. It does not depend on the brightness of one particular galaxy. Instead, it relies on a pattern across many galaxies. That makes it more robust and more deeply connected to the structure of the universe as a whole. It also ties together two distant chapters of cosmic history: early sound waves and late-time galaxy maps. An ancient ripple becomes a modern measuring tool. Another clue comes from galaxy clustering itself. Galaxies do not sit randomly in space. They cluster because they formed in regions where matter was already slightly denser. Gravity then amplified those small differences. So when astronomers measure galaxy clustering, they are indirectly measuring the underlying distribution of matter. including the dark matter we cannot see. Clustering changes with scale. On small scales, it reveals groups and clusters. On larger scales, it reveals the broader cosmic web. And clustering also depends on the kind of galaxy being measured. Some galaxies are more strongly associated with dense environments. They are what astronomers call more biased tracers. By comparing different populations, researchers learn how galaxies occupy dark matter halos and how that relationship evolves over time. So this is not merely a count of where galaxies are. It is a way of inferring where mass is and how it gathered. The visible universe becomes something like tracer dye, floating through a much larger, mostly invisible sea, and the patterns it draws are full of meaning. There is one more subtle method that adds to this picture: weak lensing. Most gravitational lensing is not dramatic. It is not always rings and arcs. Often it is much quieter. A tiny systematic stretching in the shapes of distant galaxies, caused by the accumulated mass between them and us. Any single galaxy has its own natural shape, so by itself, one galaxy is noisy evidence. But if you measure millions of galaxies and look for a shared directional distortion, a signal begins to emerge. That shared stretching maps the large-scale distribution of mass, including dark matter. It is a little like sensing a faint current in a river, not by touching the water directly, but by watching how countless leaves drift together. And this is part of what makes astronomy so satisfying. The objects remain what they are: far away, ancient, quietly shining. What changes is us, our patience, our precision, our ability to ask better questions. And with each improvement, the universe becomes not smaller, but deeper. Weak lensing is one of astronomy's quieter achievements. It asks a great deal from the observer. The images must be exceptionally sharp. The instruments must be carefully calibrated. And tiny distortions introduced by the telescope itself must be corrected with great care. Only then can the signal emerge. But when weak lensing is measured well, it becomes one of the cleanest ways to weigh the universe. It does not ask matter to shine. It asks matter to bend light. And from that bending, astronomers can build a map of mass. That map can then be compared with maps of galaxies. Where the two match, and where they do not, teaches us how visible matter and dark matter trace one another across cosmic time. Sometimes lensing becomes stronger, much stronger. When the alignment is just right and the foreground mass is enormous, background galaxies are stretched into bright arcs. Sometimes they are even split into several separate images. These are the beautiful, dramatic cases of strong lensing. And they are more than beautiful. They are precise. The exact positions and shapes of those arcs depend very sensitively on the gravitational field of the lensing object. So by modeling them carefully, astronomers can reconstruct the mass distribution of a galaxy cluster. This is especially striking because clusters contain far more mass than what is visible in their galaxies alone. Much of that mass is dark matter. Strong lensing can even reveal smaller clumps of mass inside the cluster. Tiny irregularities, substructure, hidden concentrations that subtly alter the images in measurable ways. And sometimes lensing gives one more gift. It magnifies a distant background galaxy so strongly that astronomers can study it in detail when it would otherwise be too faint to examine. So one phenomenon provides two rewards at once. It weighs the foreground cluster and reveals the background universe. It turns geometry into a measuring tool and it helps us understand how matter is arranged in the largest gravitationally bound structures in existence. Galaxies themselves are not always oriented randomly. Their environment can leave a mark on how they spin and how they point through space. In dense regions and along the long filaments of the cosmic web, galaxies can show faint alignments. These alignments seem to reflect the tidal forces that shaped them as they formed. As matter flows along the web, it can tug on a growing galaxy and gently nudge its rotation into a preferred direction. Later encounters may strengthen that tendency or disrupt it, depending on how crowded the neighborhood becomes. The effect is subtle, so subtle that astronomers need careful statistics to detect it. Chance can imitate a pattern. Noise can hide a real one. And yet, the signal matters. It matters first because it tells us that galaxies and the cosmic web grow together. And it matters second because these natural alignments can interfere with weak lensing studies. Weak lensing also creates alignments, so the two effects must be disentangled. That makes galaxy orientation both a scientific clue and a calibration challenge. The environment shapes more than which galaxies live near each other. It can also leave a fingerprint on how they are angled in space, as though the cosmic web itself has a preferred grain. Inside galaxy clusters, environment can do something even more direct. It can strip galaxies of their gas. A galaxy cluster is not empty between galaxies. It contains very hot, thin gas spread across the cluster. And when a galaxy moves through that medium at high speed, it feels something like a wind, a pressure, a force. Astronomers call this ram pressure. That pressure can push gas out of the galaxy's disk, especially the more weakly bound gas in the outskirts. In some cases, galaxies are seen with long tails of stripped gas trailing behind them, like banners in a storm. This matters because gas is the raw material for star formation. If the gas is removed, the galaxy's future changes. Taking away the gas is like emptying the pantry, and this can happen relatively quickly. One fast pass through a dense part of the cluster can do serious work. Astronomers study these stripped galaxies in many wavelengths because the displaced gas can glow differently depending on its temperature and density. So the cluster becomes more than a setting. It becomes an active force. A galaxy entering a cluster is not merely joining a crowd. It is entering a place where the medium between galaxies can reshape what that galaxy is able to become. As the cold gas disappears, star formation begins to fade. The galaxy does not turn red overnight. The bright blue stars already present continue to shine for a while. But those stars live short lives. As they die away, the galaxy becomes dominated by older, redder stars. Its color slowly shifts, and over time, a once blue galaxy can become red and quiet. Clusters often contain many such galaxies. Systems that look older and calmer than similar galaxies living in emptier regions of space. Sometimes the same fading can happen more slowly through starvation. In that case, the galaxy keeps its disk for a long time, but stops receiving fresh supplies of gas. The fuel gradually runs down. But stripping is more abrupt. It can leave asymmetric gas disks, one-sided tails, and other visible clues. By combining those clues with a galaxy's position and speed inside the cluster, astronomers can reconstruct the sequence of events. The color change becomes the visible result of an invisible process. And it shows something important. A cluster does not need to smash a galaxy to transform it. Sometimes it simply blows the fuel away. Some distant galaxies are surrounded by something even more mysterious. Huge halos of glowing hydrogen known as Lyman alpha blobs. These objects can look like vast hazy clouds wrapped around young galaxies. sometimes extending far beyond the visible starlight. The glow comes from hydrogen releasing a specific kind of ultraviolet light. Light that reaches us shifted into longer wavelengths by cosmic expansion. What makes these blobs so fascinating is their scale. The glowing gas can spread across regions large enough to contain an entire galaxy group. In an image, the bright central galaxies may appear as small knots, while the surrounding hydrogen halo spreads outward like luminous fog. Astronomers study these shapes to understand how gas is arranged around forming galaxies, and how that gas connects to the larger cosmic web. Some blobs appear in crowded regions where many galaxies are assembling at once. That suggests they may be signposts of especially energetic growth, almost like neon outlines around otherwise invisible surroundings. But the real mystery is not just that they glow. It is why they glow so strongly over such enormous volumes. One possibility is intense star formation. Hot young stars can flood nearby gas with energetic photons, exciting the hydrogen. Another possibility is an active black hole. A feeding central engine can pour out radiation that lights the gas from within. A third possibility is cooling gas. As gas falls into a halo and loses energy, some of that energy may emerge as hydrogen emission. And the puzzle becomes even harder because these mechanisms can overlap. Hydrogen light can also scatter, making the glow appear more extended than the true energy source. So astronomers investigate these blobs like detectives. They compare wavelengths. They study line shapes. They search for other emission features. And in the best cases, the blob becomes a mystery story with several suspects, and evidence written in faint, extended light. At the centers of many galaxy clusters, one galaxy often stands out, larger than the rest, brighter than the rest, a giant in the crowd. These brightest cluster galaxies usually sit close to the deepest part of the cluster's gravitational well. That central position is not an accident. Over long timescales, galaxies moving through a cluster lose orbital energy through repeated interactions. The most massive galaxies are especially likely to sink inward. As smaller companions spiral closer, they can be accreted. Their stars are added to the outskirts of the central giant. And over time, that produces an enormous galaxy with a broad, faint envelope that blends into the cluster's background glow. These central galaxies are useful because they help trace the cluster's structure. Their location often marks the cluster center, and their properties reflect a long history of growth in a dense environment. When you look at one, you're seeing the outcome of many slow gravitational negotiations, a center that gradually collected what the cluster offered. There is also light in clusters that belongs to no one galaxy, a faint glow between the galaxies themselves. This is called intracluster light. It comes from stars that were stripped away during close encounters, mergers, and tidal interactions. Once freed, those stars no longer orbit a single galaxy. They orbit the cluster as a whole. That makes intracluster light both delicate and revealing. It is difficult to observe because it is spread thinly across a wide area and can easily be drowned out by brighter sources. But when astronomers detect it, it acts like a fossil record. The amount of this stray light, and the way it is distributed, can reveal how violently the cluster was assembled. It can show whether galaxies were frequently torn apart, whether the cluster recently merged with other groups or clusters, and by studying the colors of the light, astronomers can infer what kinds of stars were stripped away. It is a haunting idea. A galaxy cluster can contain wandering stars, living in the spaces between galaxies. And then there are galaxies that seem almost unreal, ultra-diffuse galaxies. These are galaxies that can be physically large, yet so faint that they nearly disappear into the background. They spread their light so thinly that they look like ghostly smears of starlight. Easy to miss, easy to overlook. And yet, they are real structures, quietly existing at the edge of visibility. Instead of showing a bright core and crisp, obvious structure, these galaxies spread their light so thinly that they look almost like watercolor brushed across the sky. That makes them easy to overlook, and it makes their existence feel a little surprising. How can something so large and so faint avoid collapsing into a denser, brighter form? One clue is that these galaxies often live in difficult environments, including galaxy clusters, where interactions and heating can reshape their gas and slow the formation of new stars. Another clue is in the way their stars are distributed. The stars are spread far apart, suggesting that these galaxies followed a different path of assembly or a different set of internal dynamics than the more compact dwarf galaxies we usually imagine. Astronomers find these systems through deep, careful imaging that can detect extremely low surface brightness features. And once they are found, they raise a fascinating question. Are they failed giants that never formed many stars? Or are they puffed-up dwarfs, reshaped by their surroundings? Their faintness is not emptiness. It is a signature. Ultra-diffuse galaxies can still contain large amounts of dark matter despite their ghostly appearance. Some of them look as though they should be fragile, yet they survive in environments that would tear apart a truly lightweight system. That durability suggests that something unseen is helping hold them together. Astronomers test this by measuring the motions of stars or by counting and tracking globular clusters orbiting within the galaxy's gravitational reach. If those tracers move faster than the visible stars alone can explain, it suggests the presence of a substantial dark matter halo. That creates a striking contrast. The galaxy's light is thin, but its gravity can still be strong. This challenges simple assumptions about how starlight relates to mass. It also opens several possibilities. Some ultra-diffuse galaxies may be extreme examples of ordinary galaxy formation in which star formation was unusually inefficient. Others may have lost their gas early, leaving behind a faint stellar population inside a massive halo. Each case helps refine our models because it forces us to separate what we see from what truly shapes the system. Some galaxies are almost pure gas, with surprisingly few stars. There are systems where starlight is minimal, yet the gas reservoir is enormous. In these galaxies, the usual story of gas quickly turning into stars seems to have stalled. The gas may be diffuse, spread out, and stable against collapse, making it harder for dense star-forming clouds to appear. Low metallicity can also contribute, because fewer heavy elements make cooling less efficient, and cooling is an important part of the path toward star formation. Some of these galaxies are first discovered through radio surveys that detect neutral hydrogen long before the galaxies stand out clearly in visible light. They are fascinating because they feel like galaxies waiting to begin, or galaxies that began and then hesitated. They also serve as laboratories for understanding what star formation requires and what can prevent it, even when raw material is present. If you want to know why galaxies light up, it helps to study the ones that remain mostly dark. Other galaxies are rich in stars but poor in gas, showing that their fuel was either exhausted or removed. A gas-poor galaxy can look luminous and settled, yet it carries a quiet warning. The supply line is gone. Some galaxies slowly use up their gas over long stretches of time, turning much of it into stars until the remaining reservoir becomes too small to sustain further star formation. Others lose gas through environmental processes, such as stripping inside clusters or through energetic internal events that heat or expel the gas. The result is a system where the stellar population dominates, while the usual signs of ongoing starbirth are weak or absent. Astronomers identify gas-poor galaxies by looking for weak radio signals from hydrogen, by measuring low molecular gas content, and by examining spectra that lack strong emission from star-forming regions. These galaxies matter because they show that galaxy evolution has off-ramps. A galaxy can move from building to aging, not because stars stop shining, but because the conditions needed to make new ones have been shut down. The stars remain as a record of past abundance. The missing gas hints at what changed. Galaxy rotation curves helped reveal dark matter, one of astronomy's most important surprises. The surprise was not simply that galaxies rotate. It was how their rotation behaves with distance from the center. Astronomers expected the outer regions to slow down because most of the visible mass is concentrated near the middle. Instead, measurements showed that the outer parts often keep moving quickly. This result came from careful studies of the motions of stars and gas, including radio observations of hydrogen that extend well beyond the bright stellar disk. The implication was difficult to escape. There must be additional mass spread widely around the galaxy, far beyond what the light alone suggests. This idea reshaped modern cosmology because it implied that the universe contains a dominant component that does not glow. It also changed the way astronomers think about galaxies themselves. A galaxy is not only its stars, it is a luminous core embedded within a much larger gravitational structure. The rotation curve became one of the keys that unlocked this hidden majority. The Tully-Fisher relation links a spiral galaxy's rotation to its brightness and mass. Spiral galaxies show a remarkable pattern. The faster they rotate, the more luminous they tend to be. The connection is not perfect, but it is strong enough to be useful. Astronomers can measure a galaxy's rotation speed from the width of its spectral lines, then use that relation to estimate how intrinsically bright the galaxy should be. By comparing that intrinsic brightness with how bright it looks from Earth, they can infer its distance. That makes the relation an important rung on the cosmic distance ladder, especially for mapping the nearby universe beyond our immediate neighborhood. It also hints at a deeper order in galaxy formation. Rotation speed reflects the gravitational pull of the galaxy's total mass, including its dark matter halo. Brightness reflects the amount of starlight. The fact that these two track one another suggests that star formation and halo structure are linked, even if the details are still being refined. It is a bridge between what we can measure easily and what we want to know. Elliptical galaxies follow a different rule, one in which random motions support the stars. In a spiral galaxy, the disk is supported by rotation, with stars moving in an organized swirl. In an elliptical galaxy, support comes from something more like the motion of a crowded city square. Stars travel along many different paths, crossing in all directions, and that random motion provides the pressure that balances gravity. Astronomers reveal this by taking spectra across the galaxy and measuring how broadened the stellar absorption lines are. Broader lines mean a wider spread of stellar speeds. This difference affects how ellipticals age and how they respond to encounters. Without a thin, orderly disk, there is less obvious structure to disturb. Even so, elliptical galaxies can still preserve subtle clues, such as shells and gradients, that hint at their assembly history. Once you understand the role of random motion, an elliptical stops looking like a smooth blur. It becomes a dynamic system made of countless stellar journeys woven into one steady glow. The fundamental plane ties an elliptical galaxy's size, brightness, and internal motions together. Elliptical galaxies may look simple, but they follow a surprisingly tight relationship. If you know how large an elliptical is, how its light is spread across that size, and how fast its stars are moving inside it, those three quantities line up on what astronomers call the fundamental plane. This is not a literal plane you can see. It is a mathematical pattern that suggests elliptical galaxies are governed by shared physics and that their structures are not arbitrary. The relation likely reflects the way gravity, mass distribution, and stellar populations work together after a galaxy settles. Astronomers use it both as a diagnostic and as a tool. If a galaxy falls off the plane, it may have had an unusual history or an unusual stellar population. If a group of galaxies sits neatly on it, that suggests the system has reached a kind of equilibrium. It is like discovering a hidden rulebook beneath a smooth appearance and realizing that the calm light is supported by consistent internal order. Some galaxies contain globular clusters that are older than most of the stars in their disks. Globular clusters are dense, ancient groups of stars that orbit a galaxy like a swarm of tiny satellites. Many formed very early, when the universe had fewer heavy elements and galaxies were still assembling their main structures. That means a galaxy can carry these clusters as relics from its earliest phases, even if the disk continued forming stars much later. When astronomers study globular clusters, they often find stellar populations that are remarkably uniform in age, and they can measure their chemical composition to infer how early those clusters formed. These systems are also resilient. Their tight gravity holds them together across cosmic time, allowing them to survive mergers and upheavals that can reshape a galaxy's disk. In a sense, they are fossils that move. They travel through a galaxy's halo while preserving a memory of conditions that no longer exist in quite the same way. When you observe a globular cluster system, you're seeing a galaxy's deep past still intact and still in motion. The number of globular clusters can also hint at a galaxy's dark matter halo. Counting globular clusters is not only a census of star clusters, it can also provide a clue to a galaxy's total mass budget. Across many galaxies, astronomers have found that richer globular cluster systems tend to be associated with more massive halos, including the unseen mass that dominates the outskirts. The idea is that building or retaining many globular clusters is easier in a deeper gravitational well, especially early on when conditions were turbulent and gas was still being gathered. This correlation is useful because globular clusters can be easier to identify than the faint outer halo of stars, and they can be traced to large distances from a galaxy's center. Astronomers use deep imaging to find these compact ancient points of light, then confirm them through their colors and motions. The relationship is not perfect, and it can vary with environment and history. Even so, it offers another way to connect visible structures with the larger invisible framework surrounding a galaxy. Still, it offers a clever shortcut. Tiny clusters of stars can act like signposts, small visible markers for a much larger invisible structure. By counting them, by watching how they move, astronomers gain a way to estimate a galaxy's hidden weight from the company it keeps. And from there, the story becomes even stranger. Some galaxies contain counter-rotating disks. In a typical disk galaxy, most of the stars and gas orbit in the same direction. Everything joins the same broad turning motion, like traffic moving around a circular road. So it is startling to find a substantial component moving the opposite way, like two rivers flowing through each other. This kind of counter-rotation is difficult to create from within. Usually it points to something that came later, gas captured from a neighbor, or material accreted from the surrounding environment, arriving with a different angular momentum, Over time, that acquired gas can form new stars, and those stars inherit the opposite spin, so a secondary disk grows inside the first, carrying a different history in its motion. Astronomers detect this by measuring Doppler shifts across the galaxy. They trace how velocity changes from one side to the other, and then they find the reversal. Sometimes the counter-rotation appears in the gas alone. Sometimes it appears in the stars as well, and each version tells a slightly different story about timing, mixing, and when the outside material arrived. That is what makes these systems so fascinating. They make history visible in motion. A galaxy's present-day rotation becomes a record of past encounters, a quiet reminder that galaxies can be rebuilt from the outside in, without always looking obviously disturbed in an ordinary image. At the hearts of some galaxies, there is another surprise. Not a black hole, not an active nucleus, but a compact, brilliant knot of stars packed into a very small region, a nuclear star cluster. These dense central clusters can contain multiple generations of stars. That suggests they grew gradually, through repeated inflows of gas, and through the inward migration of smaller clusters. Their gravity can dominate the very center of the galaxy. They shape how stars move. They influence how gas settles. And in some galaxies, a nuclear star cluster and a central black hole may even coexist. The balance between them can change with galaxy mass and with history. Astronomers study these clusters by resolving the central light as clearly as possible, and by measuring stellar motions to estimate how much mass is concentrated there. The result is a different kind of galactic core story. Not every center is ruled by one dark object. Some are ruled by an intense crowd of stars, bright enough to stand out, and massive enough to reshape the inner city of the galaxy. Many galaxies also seem to have grown from the inside out. That means the central regions formed earlier, and the outer disk developed later. Fresh gas settled at larger and larger distances. The center matured first. The edges filled in afterward. This kind of growth leaves age gradients. The inner regions tend to contain older, more metal-rich stars. The outskirts are often younger, and when fuel remains, more actively forming stars. Astronomers test this pattern by measuring stellar ages and chemical compositions across a galaxy's radius. They use spectra. They use multicolor imaging. They separate one stellar population from another, and they ask how star formation shifted over time, from compact central bursts to more extended activity across the disk. Inside-out growth helps explain why many galaxies have dense inner regions and more delicate outer structures. It also connects naturally to angular momentum. Gas with higher angular momentum tends to settle farther out, so later arriving material extends the disk almost by design. If you picture inside-out growth, you can imagine a city expanding outward from an old downtown. The center becomes established first. The outer neighborhoods come later, and the whole galaxy is built in stages, not all at once. The first galaxies in the universe helped shape everything that came after. Those earliest galaxies did more than shine. They changed their surroundings. Their stars produced intense radiation that altered intergalactic hydrogen. Their winds and explosions pushed material outward, spreading the first heavy elements into the space between galaxies. Those elements made cooling easier. They helped dust form. They opened new pathways toward more complex structures. Early galaxies also shaped the cosmic environment through gravity. They gathered matter into the first nodes of the cosmic web. They influenced where later galaxies would grow. Even their black holes may have helped seed later generations of active galactic nuclei. affecting how gas behaved in young halos. So when astronomers search for the first galaxies, they are searching for beginnings that echo forward. Later galaxies inherited more than mass. They inherited conditions. They inherited enriched gas, a changed radiation background, and a web of structure already partly built. In that sense, the first galaxies are not just the earliest chapters. They are the opening scene, setting the lighting and the mood for everything that followed. And studying distant galaxies is one of the ways we learn what our own galaxy may once have been. We cannot rewind the Milky Way like a film. We live inside it. We see it only in its current state. But distant galaxies offer earlier versions of similar processes. By comparing galaxies across cosmic time, astronomers can infer how disks assemble, how bulges grow, how star formation rises and falls, and then ask, which pathway best matches the galaxy we call home? Distant galaxies also show us what the Milky Way did not become. Some galaxies quenched early. Some grew into giant ellipticals. Some remained small and irregular. Those contrasts help narrow down our own galaxy's likely history. There is also a practical advantage. External galaxies let us measure structures directly. Bars, rings, interactions, in ways that are much harder to see from inside a disk. Each faraway galaxy becomes a kind of natural experiment, a proxy, a way to explore possible versions of our own past using the universe's variety as data. So the story of distant galaxies is also, indirectly, a story of where we came from. And every new deep survey adds more galaxies to that story. It also adds more questions. Astronomy moves in a rhythm. A new survey reaches deeper, or wider, and suddenly the universe looks more crowded, more structured, more surprising. A deeper survey finds fainter galaxies and rarer kinds of systems. A wider survey shows how environments change the story, from dense clusters to quiet voids. Each increase in sample size strengthens what we think we know, but it also reveals outliers, and those outliers often force new ideas. Sometimes the new questions are about physics. How efficiently did gas turn into stars in the early universe? Sometimes the questions are about measurement. Has dust fooled us? Has lensing altered what we think we see? Either way, the map grows, and the edge of the map becomes the most exciting place to stand. Deep surveys also create shared fields that astronomers return to again and again. They revisit the same sky with new wavelengths, new instruments, new techniques, and over time, those regions become living archives, places where the universe keeps offering more detail, and where every answer invites a sharper question. And now, as this journey comes to a close, the universe may feel a little wider than it did before. We drifted past distant galaxies shining from ancient time. We followed light carrying their stories across immense space. We lingered over crowded clusters and delicate streams of stars, over hidden gas clouds, and dusty regions where new suns are born out of sight. We followed gravity as it bent light into arcs and rings. We listened for the deeper patterns revealed by surveys, where galaxies gather along the cosmic web like pearls on invisible threads. And through all of it, there was that steady sense of perspective. Each faraway glow is not just a place, it is a preserved moment. A message arriving after an unimaginably long journey. Some galaxies grow through calm accumulation. Some are reshaped by encounters. Some blaze fiercely at their cores. Some fade into slower, older light. Together, they tell one long story of change, written across the sky. Now, you do not need to hold on to every detail. You can let the ideas settle, like starlight sinking below a horizon. Let your jaw unclench. Let your shoulders soften. Let your breathing find an easy rhythm, and let the universe grow quiet again. Rest here for a moment, in the calm after the cosmos. Sleep well. Good night.